What is the electron configuration for cobalt? 27 protons, symbol CO. Now, most people learn based upon what's called the strict aufbau filling method. Now, aufbau is German for that filling order. And effectively, it's a set of abstract numbers, 2, 6, 10, and 14, which fills in these sort of diagonal patterns. So you get the 2 in shell 1, then you get 2, then 6 in shell 2, 2, then 6 again in shell 3, but then 2, strangely enough, 10, then 6, 2, 10, 6, 2, 14, 10, 6, as you go through these different shells. Now this is very abstract, and it has its rules. First, partial subcell filling is allowed. Second, there is that fill order I described. The first is the 2 subshell S. Then it goes to the 14 electron subshell F. Then the 10 subshell D, and then the 6 subshell P as last. So this order is very strange. The second rule is that the subshell D fills in the order with N, but its energy is actually N minus 1. And the F fills with N, but its energy is N minus 2. Now remember these same rules, because we're actually not going to change them, but we're going to explain them with 3D engineering. So first, subshells, to me, are longitudinal rings of electrons. That is, they're at the same inclination angle, like on an hemisphere, at the same distance, and thereby have the same energy. They're also in two hemispheres. Around a nucleus, there's a set in one hemisphere and a set in another. And this is my interpretation of Bose's proof of statistical mechanics in his 1924 paper that led to his winning the Nobel Prize. And it includes what he called cylinder surface, and he added a 2x factor, which he called polarity. Well, there it is. Two hemispheres, polarity, and the cylinder surface. This is like the end cap rim of two cylinders around on either side of the nucleus. And that is the engineering logic that we use, that I use in explaining all electron rings, chemistry, and physics. So now it gets a little more complicated as you have many layers. It's not this simple set of easy lines, but it's really 3D engineering. It's a 3-vector, 2-hemisphere method of using the field acceleration physics stack. So the first shell, obviously, when you have one on this things, and this is the lower hemisphere, and there's another set. Further, the counts go 1, 3, 5, 7, but that is really a ring of 3, a ring of 5, a ring of 7, and down here another ring of 3. Now, these prefer to be on the axis, so the ones on the poles line up, and these ones become subshell S with 2, 1 electron in 2 hemispheres. Now that leaves you with the final point, and that is, as you go away off axis, these two can interlace in the 2 hemispheres by being offset by 1/2 phase, 180 degrees. And thereby, they fit a little tighter. So the structure of an atom is actually a little longer on the axis, the nucleostatic axis, than it is at the rim. So the distance out here, thereby the release energy of this, is more like this 1, 2 layers in, just like an aufbau. Now, I actually can make this easier because this 3D structure then changes the rules for how we make electron subshells. First, there's two hemispheres, a set in one hemisphere and another. Second is only full subshells are allowed. There are no partials, because unless you have that, you don't have the Bose cylinder surface, which means you don't have statistical mechanics, and you don't have everything that we know to work regarding electrons. Electrons do not settle in partial shells. That part of strict aufbau is wrong. Now, obviously, if you're all the way full, it doesn't matter if they are full. And the other piece is that there's a transitional equatorial subshell that has up to 3. Now that is not in either hemisphere, so its 3 count does not double. And this becomes the electron exceptions for configurations when you have odd counts. So that you can have 2s and balance across the hemispheres, and a 3 so you can pick up those extra structures that are odd counts. Now, there is a preference for filling. First, you want the tightest fit. You only want full subshells. And then you want to do pole to equator. You much prefer by the weak force to be pulled in towards the pole. And of course, as I said, that D shell fills in order, but it's slightly closer in than these. Now, I call this diagram the Arno-Diagram. It's what we use for every one, and there's one for each shell, for the outer layer. This is the template for subshell, for shells 4 and 5. So for the one today, I'm talking about 27 count CO symbol cobalt. Now, the strict aufbau rule would say that you do 2s7, then you jump to that D, and you do a partial 7 of 10. And that's the same thing they show in Wikipedia. However, by that logic, you have partials. By the Arno-Diagram, which is the 3-vector 2-hemisphere structure, you have nothing in the S. You have 4p, p6, the 3 here and the 3 here. Notice that they are offset by half phase, okay? The meridian is down here versus up here, so that they are at 180 degrees versus the nucleus. And then you have the 3 equatorials, 1, 2, 3. So with this diagram, you always fill out this bottom part that says 0 plus 3 plus 0 plus 3 plus 0 plus 3 plus 0 equals 9 outer shell electrons, all full, and this becomes a stable atomic shell for this electron configuration, and thereby also becomes the placement for that. Now, why does my method work versus others? Well, you can get some idea about this by chemical properties. You see, there's a nucleostatic axis. That is the preference for, that's the alignment that everything wants to be pulled towards. But of course, if all 3 are pulling towards that, they set up into a ring around that. However, they also want to align. So if you have ones in this shell, they align for magnetism, but as you can see, there's not a lot of other spacing, so they block conductivity. However, if you have electrons in this equatorial, they are spaced outside of other electrons, so it's easy for them to move in and out, and thereby they have high electrical conductivity. But if their axis is pointing towards the nucleus, that's at a perpendicular and thereby interferes with global permanent magnetism. So these typically, when they have this, block magnetism. And so I choose this electrical conductivity, and this diagram tells me that this will not be magnetic, but will be highly electrical conductive. And that's what we find in the properties of cobalt.